Hey there, this is Sarnath. In this video, I am going to show you how EMI calculations are done, what is the mathematics behind it, and how an amortization schedule is prepared. So this will help you understand completely how EMI calculations are done. Consider this scenario. Let's say that the amount borrowed is $5 million at an interest of 5.8% per year with a tenure of 10 years. And in this video, I am going to assume that the payment is made only once per year, right? We can actually calculate it for 12 months as well, but that will simply complicate the illustration. So to keep the illustration simple and to the point, I have assumed that the payments are made once per year. So let's take this 5 million and divide into 10 parts. Why 10 parts? The repayment is going to happen over a period of 10 years. So every year we will repay 500,000 of it. In 10 years we will repay 5 million, right? Now think from the lender's angle. Let's say that I have lent $5 million to somebody. At the end of first year, he is giving me 500,000, which means that $5 million was with the borrower for one full year. So the interest that I would calculate for 1 year would be 5 million into 5.8 percentage, because that is the assumed rate of percentage, which will give me $290,000 for that year. Okay, so now he has paid me $500,000. The next year he comes and pays me another $500,000. Now what should be the interest? Now for this year, if $5 million was not there with him, he had only $4.5 million because he has already paid me $500,000. So I have to think that for $4.5 million, what is the rate of interest? So I multiply that with 5.8 by 100, which is our assumed rate of interest, and calculate the interest as $261,000. This method is very simple and it will yield us an amortization schedule like this. If you focus on the last column, which is the yearly payment, it keeps on changing. It starts with 7,90,000 or 790,000, then it goes to 761,000, and finally at the 10th year it is at 529,000. This yearly payment is not constant. Is that a problem? What is the problem with the variable yearly payment, right? Theoretically, it's all good, right? But practically, people will complain about ever-changing payment. Some people will voluntarily pay the previous year's payment or previous month's payment and say, hey, you know what, I forgot, right? There's a productivity loss in dealing with payment-related issues. It's an unnecessary headache for the bank as well as to the banking customers. So the idea is, can we make this constant somehow? So that is what we are going to see in the coming slides. Please allow me a small digress here. So the same thing holds good for data scientists as well. So when data scientists present their results to business teams, it needs to be in business vocabulary, right? If you put too much technical jargon in that presentation, they are going to say, oh, we don't trust you, man, right? That kind of issues start creeping in. So the fundamentals is the same. When you communicate things to external world, you should ensure that all your technicalities are closed and they are not visible to others, right? It's all packaging. Let us relook at our earlier amortization schedule. Look at the first column, balance, right? It keeps coming down, and because of that our interest calculation goes down and our principal remains constant at 500,000, right? Now the variability comes from the loss of interest. The question is, can we compensate the loss in this interest? Can we increase the principal to compensate for loss in interest? That's the question that we would like to address. And the only constraint for the principal is that it should add up to the original amount loaned. There is no rule that says that principal cannot be variable. We can make it variable as long as the yearly payment is constant. No, there is no questions asked about principal, right? So let's exploit this and see if we can get to that point. Let the loan amount be called as L. In the first period, right, the opening balance is L. We are looking at the principal for this period as P1, some principal P1. We have to find this out. And the interest paid for the first period is the complete amount L multiplied by the rate of interest. That would be the interest I would charge. So in our case, it's 5 million into 5.8 percentage, which is $290,000. Right? That would be the interest for the first period. This is pretty simple. For the second period, the opening balance is no more L, right? It's L minus P1. We don't know what that P1 is yet, but that's my P1. And the principal for the second period, let's call it as P2, and the interest is L minus P1 into R, right? Because L minus P1 is the remaining balance, right? Now, what we want to do, we want constant payouts, which means that if I add P1 with the interest paid in the first period, it should match up to P2 plus interest paid in the second period. So if you look at the right hand side of the slide, you can see that we are equating P1 plus L into R with P2 plus L minus P1 into R. L into R and L into R gets cancelled. You get P1 is equal to P2 plus P2 minus P1 into R. So ultimately you see that P2 is equal to 1 plus R into P1, which means that P1 gets increased by R percentage to get P2. So that is the equation. Let us pause and analyze what has happened. The interest of the second month was L minus P1 into R. We saw that. Compare this to the interest of the first month, which was L into R. So the loss of the interest is P1 into R. To compensate this loss of interest, we add this to the principal P1. So P1 plus P1 into R gives you P1 into 1 plus R. This is the same exact result that we saw before. I'm just presenting it so that it's more understandable and intuitive. So the question is, what is P3 now, right? We can apply the same logic. P3 has to be P2 into 1 plus R, right? The same logic. So we just expand P2 as P1 into 1 plus R. So that gives me P3 is nothing but P1 into 1 plus R whole squared, which means that it is just compounding. It's the same formula for compound interest, 1 plus P into 1 plus R by 100 whole power n. We have all studied that. It's the same thing. It is just compounding. The principle is just compounding. That is the whole idea behind this too. So if you have to maintain equal monthly installment or yearly in our scenario, the principal portion of the payout must compound at the interest rate R. So let us go and verify this result with this result that we have got, that the principal must actually compound, right? So I just went to calculatestuff.com. I found the loan amortization calculator here. So I fed in the values. The loan amount is $5 million. I hope it is 5 million. Yeah, it is $5 million. Interest rate at 5.8. Term is 10 years. So let's see what it reports. Now in this screenshot that you see, the amortization schedule focused on the second column, which is the principal column. What we want to find? We want to find if those numbers, this increasing set of numbers, are actually compounding at 5.8 percentage, right? Now since this, if you look at the first column, it's all monthly schedules. So 5.8 percentage holds for an year. For a month, it has to be 5.8 by 12. So I just worked out the math that you see here in that dark box. If you focus on the top row, which is like which is in smaller font, you can see that I have put 30,842.74 into 1 plus 0.058 divided by 12 raised to the power of 7. Why 7? October 2020 is 7 entries away from March. You have to consider April as 1, May as 2, June as 3, 4, 5, 6 and 7. October is 7. So it yields me 31,901.50, which actually exactly matches with what the website has reported. So the fact that the principal is also compounding at the same rate of interest. So whatever we have found in 2 slides above is actually true. Okay, sounds good. So we see that the principals are compounding, but how do you find the first principal amount? Because the initial principal payment also determines every other principal, because it is the same initial principal that gets compounded over time, right? But we have a constraint here saying that all these principles should add up to the original loaned amount. So which means that you can see from the equation there, if you take the first principal as P1, P1 into 1 plus 1 plus R by 100 plus 1 plus R by 100 whole squared until n minus 1, that must match L, right? So that's a good complicated equation. The next slides we'll see how we can simplify that. So continuing, so you can see that first line is the same thing that we saw in the last slide. Let us use x to represent 1 plus r by 100 so that it is easy on our eyes. So that transforms this equation to p1 into 1 plus x squared until x power n minus 1 is equal to L. Now just look at this expression 1 plus x squared x cubed. If we call it as f of n minus 1, with subscript x, If we multiply this 1 plus x squared with x, again you will get x plus x squared plus x cubed until x power n. You see that there's a lot of overlap between this expression and the expression multiplied by x. We can exploit this to simplify it. So we can simply write a recurrent equation like this: x multiplied by f of n minus 1, and add a 1 to it, you get f of n, right? That is what is the relation that we saw, so that we can exploit. But we also know that f of n is nothing but f of n minus 1. F of n minus 1 is nothing but 1 plus x squared until x power n minus 1. If I add an x power n to it, I'll get f of n, right? So with both these relationships, if we solve it, what we get is f of n minus 1 is equal to x power n minus 1 divided by x minus 1. You can see the derivation here. I'm not going through the details, but it's fairly simple to follow it. So let us revisit this original equation that we had, which is p1 into 1 plus r by 100 plus 1 plus r by 100 whole squared, so on until 1 plus r by 100 whole power n minus 1 is equal to L. But we have a simpler equation now, x power n minus 1 by x minus 1, where x is 1 plus r by 100. So substituting that in the second row, we see that p1 into, instead of x power n minus 1, we have 1 plus r by 100 whole power n minus 1 divided by 1 plus r by 100 minus 1 is equal to L. So this is fairly simple to follow. After simplifying, you see that highlighted expression in blue. So let us see if we can calculate the first principal now for our scenario. In our scenario, L is $5 million, R is 5.8, N is 10, right? So with that, you can see that on the left hand side of the slide, you are calculating P1 as 382,917.3587, and the interest that we pay is for the whole amount for this first year, right? $5 million at 5.8% is $290,000. Perfect. Now move on to the second period, which is the second year in our case. The principal P2 has to be compounding at the rate. That's what we saw. So the first principal was 382,917 or 382,917. We multiply that with 1.058, we get 405,126. 405,126.55046. That would be our principal. And the balance amount, what's the opening balance is? The opening balance is 5 million minus the previous principal, right? When you work that out, you get 461,000, sorry, 4.6 million, somewhat close to 4.6 million. We are no more at 5 million, and we have to calculate the interest at this balance. 4.6 million times 0.058 gives us 267,790.7931. So now we have calculated the principal and interest for the first two periods. Can we just check if P1 plus I1 and P2 plus I2 are matching? So we just go and add them, and we find that yes, indeed, it matches. It comes to 672,917. That will be your EMI. That's it. That was interesting to note that the sum of principal and interest for the first month exactly matches with the second month and so on, and which we call as EMI. Now the question is, can we have a formula for EMI? Why not? Because we have the formula for P1, and the EMI has to match P1 plus I1, which is the interest paid in the first period, which is pretty easy to calculate because it is calculated on the entire loan amount, L into R by 100. So adding them up, we get the formula, which is highlighted in blue. And to verify, I just fired up Google and said, "Hey Google, tell me the formula for EMI." And then he threw up something on Business Today. You can see that, and the formula matches completely. So we are in business, thanks to Business Today. So to conclude, here is the final amortization schedule for the $5 million that we borrowed for 10 years or a period of interest of 5.8% per year with only annual payments and no monthly payments. So this is the interest that you see, and you can see that the EMI is constant. So that concludes this session. I hope you got an idea of how to calculate EMI. And if you like this video, please subscribe. Thank you.